Okay, hello and welcome to the third lecture to my course on Introduction to Quantum Theory and Technologies. So in the last lecture, we did some work on introducing the background to sort of the historical aspects of quantum theory. So from this week, we're actually going to get into the nuts and bolts of how quantum theory really works. So in the last two lectures, I've really just been talking only qualitatively about how quantum theory works and how it relates to everything. But what I really want to show you in this course is really how quantum mechanics actually works. To do that, we'll actually need a little bit of mathematics because, of course, quantum theory is mathematical theory, and we could just go on and talk about just how quantum theory is weird because of all the wave nature or the particle nature or all these paradoxes. But I think you can never really properly appreciate it unless you actually see it in the mathematical form, which is really what the theory is actually all about. So what I'll be talking to you today is the first of kind of two crash courses in just the mathematics that we will need. And the first thing that we'll need is to understand is complex numbers. So quantum theory, you really need this idea of complex numbers. Of course, these were invented not with this application in mind, but actually it turns out that these are really very useful in physics. So it's actually well worth learning anyway. So, okay, so let me just get started on complex numbers. So firstly, there's basically a central kind of quantity that happens or that is present in complex numbers, and this is this um, thing called I. So as we know, if you want to take the square root of a number, then it has two solutions. Say you want to take the square root of 4, then it's got solutions of plus or minus 2 because 2 times 2 is 4, or minus 2 times minus 2 is 4. Okay, but what about if you wanted to take the square root of a negative number? So, for example, here we've got this equation here. So we've got x squared plus 4 is equal to 0. So if you put this 4 on the other side, then of course then we have this equation x squared is equal to minus 4. So now we want to know what x is, so we should take the square root of minus 4, right? So of course everybody tells you in school that you can't take the square root of a negative number. So what do you do? Well, let's just suppose that there's this thing called I, and this is whatever whatever it is, it's the square root of minus 1. So let's just say we just call this thing I, and let's just see how far it will go. This is the kind of thing that mathematicians like to do, by the way, where they sort of invent new things and essentially study all the properties of it. So you sort of say, in this case, hypothesize the existence of this thing called I, and then it should obey some properties, and then from there you can derive all kinds of weird and wonderful things from it. So, so in this case, you can write down the solution to this equation. This x squared equals x squared plus 4 is 0. In this case, it's the solutions of this are equal to this. Well, because if I square this, so this is x squared, then just like I had before with the plus or minus 2, so if I square this, then this thing should be equal to 4 times by I squared, and then this thing I squared is equal to minus 1, so that has to be equal to minus 4. This thing is fading. I don't know how to stop it fading. Anyway, I think you get the picture. So x squared is equal to minus 4, and so you can see that this is the solution of that. So so that gives us the how to actually get the solution of this particular equation. But now let's take this sort of further and see what kind of properties we can give it. So the first thing that you might ask is, so if you have two complex numbers, then how do you add or multiply them? So so here what we've got is maybe a very simple addition of two complex numbers. So basically the way that you treat this is, if you're familiar with just how you do algebra, so just like if you've got the equation like 2a plus 3a is equal to 5a, you just basically treat this imaginary number as in the same way. So if you got two i's, then you write this as 2i, so 2 times I. This really means it's 2 multiplied by I. You can also subtract two complex numbers. In this case, so I minus I is equal to just 0. Or if you say if you multiply, if you subtract a complex number from something which is, say, larger than itself, then, for example, I minus 3i would be equal to minus 2i. So we can just basically just use our normal rules of sort of algebra in order to kind of add and subtract complex numbers. Now, for multiplication, well, we already had kind of a definition of what, say, this thing here is. So what is I times I? That's obviously equal to I squared. In this case, the I squared, we already know what that is because that's how we defined I in the first place. So if we have I times I, it has to be equal to minus 1. Yeah, minus 1. But so what about I cubed? Then I cubed is obviously I squared multiplied by I, right? So we already know what I squared is. That's minus 1. This part of it is minus 1. And this part is I, so this has to be equal to minus I. Similar kind of logic, I to the power of 4 is equal to I squared times by I squared. So that is equal to minus 1 times minus 1, and so that has to be equal to 1. So this is equal to 1. So that's how you add and multiply imaginary numbers. These were actually kind of simple types of complex numbers because actually they didn't involve any real component to them. So we can actually define a more general complex number, which is like a combination of a real number. So real number, that just means any number that is like, like a plus or a minus or a 0. Or it could even be, it doesn't have to be an integer. It doesn't have to be 1, 2, 3, 4, 5. So 2.3 or pi or 6.79 minus 3 million. These are all examples of real numbers. So we can make a complex number by actually combining a real number. So a, we just said that's a real number, and then this part here is I times the real number, right? So this is I times b. So this itself, this IB thing, is of course a complex number. So you can combine the real number and a complex number, and this makes a more general type of complex number. So you might say this part of it is purely imaginary. It's a purely imaginary number, and this part of it is a purely real number because it has no imaginary component if it's just A. And then this C is a more general complex number that you can make. Because these two numbers A and B are kind of like that's A is like the real part of the number, and B is the imaginary part of the number. So these symbols here, basically that's what that denotes. If you have a number C, a complex number C, then the RE brackets C, this whole term here, basically this just pulls out the part of the number which is only real, and this part, this thing here, this IM stands for imaginary. This pulls out just the imaginary part of the number. So these numbers A and B, they can be whatever number you like. And so it's actually quite natural that you can plot this on the on a kind of a graph like this, where you plot the real part of the number on the horizontal axis. This is just by convention, and the imaginary part of it on the vertical axis. And basically you say that, okay, well, you know, any number that we were talking about before we knew about imaginary numbers lies on this line here. So, you know, minus 3 million is maybe down here somewhere, and, you know, plus 1 million is here or something. So all the numbers that we're very familiar with lie on this line, but now there's a kind of a new dimension that you can have, because previously we weren't thinking about complex numbers, but you know, if we hypothesize this, you know, I thing, then we can have a complex component to the number. And so how we would visualize it is that we would say that any complex number, so this is our most general complex number, we can imagine that to be some kind of point on this plane, and this number here is, so basically each point on this whole plane here corresponds to some unique complex number. Right? So here's our number A plus BI, and in terms of the graph, we plot it so that the x coordinate is has a value A, so the value here is A, and then the y coordinate has a value B. Okay, so this is just sort of a way to sort of visualize our complex number, and you know, you can imagine all the possible complex numbers that you could possibly have being somewhere on this plane here. So let's go back to what we were doing with adding the complex numbers. So if we had two complex numbers, and say the first one is called C, and then the second one is called C dash, then we would say we wanted to add these two things. So the question is, how do you add these two things? So the way that you do this is actually a lot like how you add vectors, actually, which we'll talk about a bit later. But even if you're not familiar with it, it just follows this kind of simple rule. So what we're trying to do is add these two complex numbers, C and C prime. So, okay, let's just sort of substitute each of these things into here. So then we have the first part of it, we can actually just collect all the parts which are the real parts of the number. So that was like a and a prime. So that's the real part of the new complex number. And then the imaginary parts are this IB and IB prime. So let's just, because they've both got an I there, let's collect the I there, put brackets around that. And so this is basically our new complex number. So the real part of the complex number is A plus A prime, and then the imaginary part is B plus B prime. So if we were to plot this, basically like here's our first complex number. That's that complex number which had the values of A plus BI. So that's our thing that we called C to the left there. And the thing that we're going to add to it is actually this guy, this yellow arrow here is what we're going to call C prime. Now the basically in terms of this diagram, the x the x component of this vector is going to have a value of a prime, and the y component of this is going to be b prime. So in this case, like for example, a prime is like a positive number, and then b prime is actually a negative number. That's why it's sort of pointing down like this. Then we just go and add the a to the a prime, and then the b to the b prime, and then what we get is basically this new arrow here, which gives us our new complex number, which is c plus c prime. Yeah. So this is how you add complex numbers. So let's just do a little bit of practice here. So, you know, what you might like to do here is just to pause the video and then just see if you can work this out for yourself. I'll, you know, immediately jump onto the answer because obviously you can just pause the video there. So, for example, let's calculate C plus C prime here. Now, here's our values of C and C prime. So for this one, basically we can add to get the real part of the number, we basically just add two real parts. So there's going to be 3 plus 1, which is 4. And then we need to add the two complex parts of it. Don't forget the minus sign here. So this will be 3i minus 2i. So this will be 4 plus I. 4 plus I. So that's the answer to the first one. C plus C prime is 4 plus I. What about C minus C prime? So the real part is 3 minus 1. So that's 2. And we need to subtract the imaginary part. So it's 3 minus minus 2, which is 5. So the answer is 2 plus 5. Okay, so that's our two values of the complex, complex additions and subtractions. So just a little quiz there for you. Okay, so you know, adding and subtracting numbers, complex numbers, looks not so hard. What about if we multiplied two complex numbers? Say we've got our two numbers C and C prime again, and what we're going to do now is to figure out how you multiply C and C prime. So here I've actually already got the answer, but let me just take you through the working here. So if we've got C, then the first one is CA plus IB, okay? And the second one is A prime plus I times B prime. Okay, and so what we just do is we just go and just multiply out all the four terms, just like you do with normal sort of algebraic variables. So the first term that you get here, A prime, is a product of these guys here. So that's A and A prime. So that gives the first term here. The second term, B and B prime, so obviously comes from this pair. And then why is there a minus sign in front of here? Well, it's because they both have an I. So I times I is equal to minus I. And so this is why there's this kind of minus sign here in front of the B prime term. So the other terms just come from the other cross kind of cases. So the A times B prime term comes from this pair. So this is A and I B prime. So there's no minus signs or anything there. So this is why this one is got a coefficient of plus I. And then the final pair is B and I think I've got a typo here. So this prime should not be here. In fact, it should be here. So this B and A prime pairing. So this also has a coefficient of plus I, and so this is why this has got a plus sign here. So basically everything looks just like normal, except that the coefficient of the B prime term is actually minus. Everything else kind of looks just like normal. Okay, so let's just go through and do this multiplication in this case. So in this case, we've got 3 plus 3i. Stop the fade here. And this is multiplying by 1 minus 2i. And so we can multiply these two complex numbers out. So let's look at the first pair. So 3 times 1 is equal to 3. Okay. Let's now look at the last pair. This is 3i times minus 2i. So of course 3 times minus 2 is minus 6, but we've got also I squared, and I squared is minus 1. So instead of it being minus 6, it's actually plus 6. Okay. So that's probably the tricky one there. Okay. Now let's do the other pairs. So we've got 3 and minus 2i. So this is going to be minus 6i. And then the last remaining pair that I've got here is the two ones on the inner side. So this is 3i times 1. So that is equal to 3i. Okay. And then we can just do a little bit of simplification. 3 plus 6 is 9. And then minus 6 plus 3 is minus 3i. Okay, so the answer to that one is 9 minus 3i. Okay. For c squared, we can let's just go down here and do it. So in this case, it's 3 plus 3i. So that's the square of that. So we know how to do squares because it's always like the first number squared. So it's like 3 squared. And then the last number squared. So that's going to be also 3 I squared. And then it's like 2 times the cross of like the other two terms. So it's like 2 times 9i, which is like 18i. Okay. We can just simplify this guy a little bit because the first one is 9. This one is actually 3 times 3 is 9, but I squared making it minus 9. And then this will be 18i. So the 9's actually cancel out, and in fact here we've actually got 18i. Whoops. Okay, 18i. Okay, so that's just some simple examples there for you. So erase that. So what about other forms of writing the complex number? So there's actually another way to actually write the complex number, which is actually a really nice way to actually represent the complex number. And maybe the easiest way to think of this is exactly how you think about vectors. So remember that we were saying that any kind of complex number can be written in terms of this kind of two-dimensional plane. So each complex number is represented on this complex plane. So so every complex number kind of looks like a vector. Now, we know that a vector, which is like something with a magnitude and a direction, you can always represent the vector not only in terms of its like coordinates. So this kind of looks like coordinates, right? But you could also represent this actually in terms of its sort of the length of the vector or the magnitude and which direction it's pointing. So in this case, in this two-dimensional case, it's actually pretty easy because really the direction is determined only by this angle theta, and the length of the vector is what we're going to call r. It's called r because it looks like some kind of radius, like a radius of a circle. And we could equally actually represent the complex number in terms of this r and theta. So basically the a and the b is they can kind of specify our complex number, and equally well the r and the theta can also specify the complex number, right? So how do we relate the two? So here we've got on one side the a and the b's, and here we've got the r and the theta. So how do we relate those things to each other? So it turns out we can just relate them in exactly the way that we would do for vectors, which is basically just use Pythagoras rule and a bit of trigonometry. So for example, here this r can be related to the coordinates just through this triangle here. So we all know that this is a right angled triangle, and if it's a right angled triangle, we can just use Pythagoras rule. And from Pythagoras rule, basically the hypotenuse, which is this the long side of the triangle, can be related to the other two shorter sides just through this kind of famous formula. So r is the square root of a squared plus b squared, and remember a and b are both real numbers, so there's nothing weird about this this type of like squaring the numbers or anything like that. So that's just straight out Pythagoras rule. Now what about this angle here? How do you work that out? Well, again, you just use a little bit of trigonometry. So the tan of this angle here is equal to the opposite side, which is b, divided by the adjacent, which is equal to a. So you can just work out what this angle here is by taking the arctangent of b divided by a. So that's how you can work out sort of the r and the theta from the a and the b. So these two formulas you can relate to each other. So how do we actually write our complex numbers? So that's very nice. So we can write it. Got this big, nice picture to represent it, but we want to write down the actual complex number. So how do we do that? Well, all you have to do is you just have to rewrite the equation for a complex number in terms of these two variables. So this used to be a plus ib, of course. So we can just relate a and b to r and theta just again from this triangle here, because we know that r times cosine of theta is equal to this side of the triangle and r times the sine of theta is equal to the opposite side of the triangle. So just from trigonometry, we can kind of write this kind of so-called polar form of the complex number, right? Okay, so this actually then leads on to Euler's formula, which is really kind of a celebrated formula well, in mathematics, really. So there's a kind of a relation where you can basically write the e to the I theta of e to the I theta is equal to this kind of relation of the cosine of this angle to the sine of the angle times I. So we can decompose this exponential to the I theta into the sum of these two parts. So actually this is nothing but a very simple example of the example that we had on the previous case, where actually this r parameter is equal to 1. So imagine all the complex numbers here, where r was equal to 1. So this would obviously be a circle like this. So it's going to go off the slide a bit like this. But this circle here is the set of all the complex numbers where this r, which is this is also called the magnitude of the complex number, is equal to 1. So basically, by relating this right-hand side to that, then what we can find is that actually this cosine plus I sine theta is actually equal to this exponential of I theta. And the proof of this, actually, you can actually work this out. I'm not going to go into it in this lecture, so you can just sort of, well, we can discuss it later if you really are interested of the proof. But essentially, the proof of this goes by you can actually expand this function in terms of some kind of power series in terms of theta, and you can basically just look at the left and right hand sides of this equation, and by looking at, say, every second term here, so this is the even powers of theta, you can figure out that this is actually equal to the cosine of theta, and by looking at the odd powers of theta, you can actually relate this to the sine of theta, and you basically have this famous relation of Euler's formula. So this is said to be kind of, one of the most beautiful formulas in mathematics, basically because you can actually relate maybe 3 or maybe 4 very fundamental types of numbers in mathematics all to each other. So this E is actually equal to this special kind of number, which is called Euler's number, which is 2.7 something. And so that's a particular irrational number. Pi is some number which is like 3.14. I is this weird imaginary number that we just sort of made up. Minus I squared is -1. Of course, 1 is maybe the most basic of all numbers, and we've also got the minus sign here. So we've got kind of all these different types of numbers coming all together, and they're all related to each other in this way. So this is why it's kind of most beautiful formula in mathematics. So what this basically means is that because this cosine plus I sine theta, this is the thing that appeared 2 slides ago. So just go back there. So I wrote any complex number could be written in this form. C equals r cos theta I r sine theta. So let's just factorize the r out of there, over here. And this relation that we had with the Euler's formula means we can actually rewrite this in this form, so that actually any complex number can be rewritten in terms of this product of the r, which is like the radius of the complex number, times by this e to the I theta, which is called actually like the phase of the complex number. So so this is essentially how the sort of the final form of how you rewrite the complex number in terms of r and theta. So these are equivalent, so you can write it also like this, but this is just a little bit more compact, and we'll sort of encounter this kind of way of writing it later on. Okay, so let me just go back and just do a couple of examples here. So let's find the value of, this is the absolute value of C for this particular example. So the definition of this absolute value appears here. So this is nothing but like the radius of the complex number, the thing which I was talking about before. So this is equal to, according to Pythagoras Rule, so basically the real part of the complex number plus the imaginary part. And for this particular example, the real and the imaginary part are equal to the same value of 3. So all we have to do is just go 3 squared plus 3 squared, and this is equal to 9 plus 9, which is 18. And we can actually do a little bit of simplification there, because 18 is 2 times 9, and so this is 2 times by 9, and this is actually, that's under the square root there, 3 times square root 2. Okay, so that's equal to the modulus. The argument of C, this is, in this case, we do the arctangent or inverse tangent of B divided by A. Again, this is just from, if you can't remember these formulas, I would just recommend you drawing like a little picture like this, where this is like A, this is like B, this is the real and imaginary parts. Here's our complex number C, and the angle here is defined as that angle there. And R is basically the length of the long side of the triangle here. So in this case, just from trigonometry, we know that the angle has to be equal to the inverse tan of B divided by A. So in this case, it's inverse tan of 3 divided by 3, so obviously that's equal to 1. So that's just 1. And this has to be equal to, say, 45 degrees. Okay. So it's actually kind of obvious from this triangle here, because in this case, this is equal to 3, this is equal to 3. So this is actually like a 45-degree triangle. So obviously it's the angle, the argument here is 45 degrees. Okay. So now let's get on to a few more kind of more complicated operations. So the first one is this so-called conjugate. So first, let me just define it. So the definition is quite simple. So say you have any complex number C, so A plus BI, then what we can do is we can just define like the conjugate of this same complex number as just the same number, but like the imaginary part has an extra minus sign. So this would be the conjugate of the original complex number here. So this is like a minus b I, and all we've really done is we've just like flipped the sign of the imaginary part, right? So this just has a minus sign on the imaginary part, right? So this is what this kind of star here means. So if you see like something star, then what this basically means is that the complex number has its imaginary part changed from with an extra minus sign on it. So in the sort of real imaginary kind of way of writing the complex number, it looks like this. What about in the polar way of writing it? So I just told you that any complex number can be written in this form as well. So r times e to the I theta. So this was like the length of the vector in the complex plane. So in this case, this will be equal. The length of this vector here is equal to r, and theta is over here. So now that we've kind of flipped this from the top side to the bottom side, obviously these two triangles here are the same. And so actually this angle here really has to be the same angle, but just with a minus sign, because this time it's pointing down rather than it's pointing up. And you can see that even if this original complex number was pointing like this way, here would be the angle. Again, the conjugate would be defined as the complex number which is pointing this way, and so the angle here would still be like minus theta. So it doesn't really matter where the complex number is. It just in this case it adds an extra minus sign to the argument, which is the angle of the complex number. Actually kind of makes sense anyway, because if we just say that the act of adding this conjugate is just to replace I with minus I, because our original representation of the complex number can be written like this: r times e to the I theta. So notice this is a positive I here. Then basically all this does is again add a minus sign to the I part of it. So it kind of makes sense from two ways. You can just view it as just something that changes the sign of I, or you could view it sort of in this graphical way where you change the angle from theta to minus theta, and it still basically holds together. So this also makes sense in terms of the properties of the trigonometric functions, because cosine of minus theta is equal to just cosine of theta, whereas sine of minus theta is actually equal to minus sine of theta. Okay, so that's the conjugate. Why do we want to define a conjugate? You know, it doesn't really seem very seems like an arbitrary definition. Well, it turns out that it's actually kind of useful, because it gives you some way of actually recovering a real number from a complex number. So, I mean, you know, don't forget that these imaginary numbers are kind of, you know, sort of hypothetical kind of numbers, right? So nobody thought of complex numbers, or nobody came across a complex number sort of in real life, as so to speak. So in order to get some kind of things to do with the real world, it's often you need some kind of operation to turn a complex number into something translating to the real world, right? So this can happen in a few ways. So, for example, if you add a complex number to its conjugate, then actually this actually makes a purely real number. And so we can see this happen in this way. So say we add C and C star, which is the conjugate of C. Then what happens is, so here's C, A plus IB, and here's the C star, which is A minus IB. So obviously, if you add these two things, then this part of it just cancels out, right? So there's no more I, and you are left with just the real part of the number, which is 2A. So that's obviously a real number. In fact, actually, subtracting the complex number from its conjugate actually does something also a little bit similar, but what it does actually is to cancel out the real part. So you're actually killing off this real part of the number. In fact, you're just left with the two complex parts of it. This is plus IB because remember the conjugate has a minus here, and then a minus minus gives a plus, right? So then you get 2IB, and actually this is 2I times the imaginary part of it. So this can actually, this basically tells you how you get exactly how to do exactly this operation. If you want the real part of a number, then what you do is you just add C to its conjugate of itself, divide by 2, that basically gives you the real part. The imaginary part, what you can do is just subtract the complex number from its conjugate, then divide by 2I, then you actually get the imaginary part. So this is sort of two ways of how you get a real number from a complex number. Another way, which we'll actually also encounter, is multiplying a complex number by its conjugate. So here, say we multiply C and C star, then what you get is firstly, of course, A plus IB, that's the original complex number. Then you get A minus IB. And so if you just do the multiplication, then you'll get certainly the A squared. And this term here, you get I times minus IB. So I squared is minus I, but I times minus I is actually equal to 1, right? And then so you just get the B squared term here. And then you might go, well, what about the rest of it? Well, what happens is that this A and the IB gives the minus IAB contribution, whereas this term here gives a plus IAB term, and this actually all neatly cancels out, and this is all you get. So you only get A squared plus B. So this is obviously, there's no complex part to this number, so it actually gives a real number. But it's actually also, in fact, equal to R squared. If we can just go back to the slide, remember how R was defined. So R squared is actually just the thing, it's like the Pythagoras rule. R squared is A squared plus B squared. So just going back, so this thing here is actually equal to the sort of the radius squared of the complex number. You can actually do the same calculation in the polar representation, which is kind of neat. So we know that C could be written as R times e to the I theta, but the conjugate could be written as R times e to the minus I theta. And if you actually work out what the use your Euler's rule, then you can work out that this e to the I theta times e to the minus I theta is equal to 1. Or if you like, even simpler, remember that if you've got two exponents ax times ay, then this is actually just always equal to ax plus y. So in that case, the a here is just e, and so we've got e to the I theta minus I theta, and that is basically, in this case, in this case it gives e to the 0, and any number to the power of 0 is equal to 1. Right? So that's why these parts just give 1, and then this part just gives the r squared. So that's just another way to do the calculation. So this is kind of neat because you can actually kind of get a real number out of the complex number, and it's kind of quite often used so that we kind of have a different notation for it, and in this case we have the sort of the absolute value symbol squared is equal to exactly the same c times its conjugate. Okay, so let's just do a quick example here. So here we've got C plus C star, or C conjugate. So this is going to be equal to 3 plus 3i. I'll stop the fade from happening. Plus 3 minus 3i. Okay, and so these i's cancel. Designed to do this, so it's good. So, and then we've got 3 plus 3, which is equal to 6. So in this case, it's just equal to 6. Now let's find the absolute value squared of c. So we can just do this from the definition. So this is c times c star. So this is going to be equal to 3 plus 3i times by 3 minus 3i. We can just go through term by term. So let's do the first two terms here. So 3 times 3 is 9. Let's do the last two terms. So 3i and minus 3i. So I times minus I is 1, plus 1. And then 3 times 3, so that's 9. The two kind of combination terms, this is minus 3i times by 3, so that's minus 9i. Then the two inner terms are 3i times 3, which is plus 9i. So note how the imaginary parts again cancel out. So in this case, this is 18. Okay, so that gives you this example. So just the last thing that I can show you that you can do is you can actually also divide complex numbers. So of course, so we've gone through addition, subtraction, multiplication. Now we want to talk about division. So of course the definition is just kind of defined like this. So C prime divided by C, of course you just divide it like this. Now not much you can actually do with that expression there. It's you can't really simplify it in general, but when you write it in the polar form, you can actually simplify it a little bit more. So this is why the polar form actually is sort of maybe the preferred way to write it if you do happen to be dividing the numbers. So for example, this 1 divided by c. So this is like the denominator of this expression. So this can be written, of course, just in this way. So we know that the c can be written as r times e to the I theta. And because, of course, if you have any power expression like this. So say we've got 1 divided by ax. This is actually just always equal to a to the minus x, right? So that's just a regular kind of algebra. So just in the same way, we can just use that relation here. So this quantity here of 1 divided by r to the e minus theta is actually also equal to 1 over r times e to the minus I theta, right? So now we can do a little bit of simplifying, because this thing of division that we were trying to do here is actually just, of course, equal to c prime divided by c, which is then equal to this guy. So we've got the magnitudes of the complex number. So there's r prime divided by r, but this is the phase part of the complex number that can actually be simplified a little bit and put together in this way. So it's e to the I theta prime minus theta. So dividing complex numbers can be a little bit easier if you use this kind of polar decomposition. And another way of kind of representing it. So often what you might like to do is to, instead of having the complex number sitting here on the bottom, so if you notice over in this previous example, we had this complex number that's sitting on the bottom. Often it's a little bit easier if you actually don't have any complex numbers on the bottom. If you just got a purely real number on the bottom, can sort of simplify the expression a little bit. In this case, you can always do this by using the fact that, remember, c times the conjugate of c always gives a real number. So you can always just multiply by this factor of c star divided by c. So this thing that I've circled here is just equal to 1, right? So I've just, what I've done here is I've got 1 over c, and I've just multiplied by 1. So obviously the same number. So then the numerator of this fraction is going to be a minus ib, because that's the definition of this of the conjugate of c, and c times c star is actually equal to, just from a couple of slides ago, c times c star is actually equal to a squared plus b squared. Okay, so then we can rewrite our expression in terms of a squared plus b squared on the bottom and a minus ib. So we can actually do that kind of same trick by to always get some expression which is a real number on the bottom, even if we've got a more complicated fraction. So in this case, the fraction that I've got here is c prime divided by c. So in this case, I'm going to multiply by this factor of 1. So that's equal to 1 here. And just by doing the same kind of algebra, I can actually get an expression where there's no complex numbers on the bottom here, and the complex number is purely on the top. So this is just the equivalent way of writing it. So it's sometimes useful. Okay, so let me just go through this final example here. So here I want to simplify this value of c divided by the conjugate of c. So firstly, let's just write out what this whole thing looks like. So it's 3 plus 3i divided by 3 minus 3i. So in this case, perhaps what I'd actually immediately do is to actually get rid of all the 3's. So I could just factor out this 3 here. So in this case, it's 3 divided by 1 plus I divided by also 3, 1 minus I. and these 3's we can just cancel out, so that gets rid of all the 3's, which is certainly kind of simplifies it a bit. Now we can do that trick of getting rid of the I on the denominator. So what you can do is you can multiply this same fraction by a factor of 1. So I'm just rewriting the fraction here again, and by multiplying it by the conjugate of the number on the bottom here, we can actually get rid of the complex part on the bottom. So notice that this second part here that I'm multiplying by, so of course this thing here is just equal to 1, right? 1 plus I divided by 1 plus I, obviously equal to 1. And we can just multiply this out. So the numerator of this is actually 1 plus I squared. So this is going to be equal to 1 squared plus I squared plus 2I, because there's these cross terms, I times 1 plus I. And then the denominator of this, so we can just go through. So 1 times 1 is 1 squared, and this cross term here is minus I times by plus I, so that's actually also equal to 1. And then the two cross terms here are plus I, and then the remaining cross term here is minus I, so of course the i's all cancel out, so that's good. And let's do a bit more simplifying on the top. So 1 squared is 1, I squared is minus 1, so this plus 2I, and on the bottom it's 1 plus 1 is 2, this 1 minus 1 cancels out, and you get 2I divided by 2. Again, the 2's cancel out, and then you just get I. So that's obviously as simple as you can possibly write it. And so by doing this kind of multiplication trick by this factor of 1, you can often simplify the expression a bit more. Okay, so I think that is pretty much all I wanted to say for complex numbers. So for the homework, what I'd like you to do is just to go through the sheet on complex numbers. So I think that must be the third sheet. And there's just some extra problems there for you, just so that you can be accustomed to complex numbers if you haven't used them before. And next week we will do similar kind of thing, but this time with linear algebra. So, okay, so good luck with the complex numbers, and speak to you next week. See you later.